close this window and everyone can see the screen. Everybody on Zoom, can you hear me okay? Fine. Right. All right, well, let's get started then. Okay. So thank you so much for inviting me here. It is absolutely an honor to be here sharing some of the work that my colleagues and I have done in the channeled scabland. I found myself looking into this landscape for my PhD at UMass, and like so many other people have, I found myself falling in love with the channeled scabland landscape. I was chatting with some of you earlier, telling you that I grew up on the East Coast, and so coming out to the scabland was unlike anything I had ever encountered before. And as soon as I saw it, I felt this urge to understand how these really powerful floods that I was studying could create such a special and beautiful and otherworldly landscape. And I'm especially happy to be here sharing my work with the IAFE community because IAFE played a very important role in my PhD research. Some of the IAFE folks came out to help us in the field, find some very large granite boulders and arrange some field sampling permissions and keep us company while we were doing some of our field work. It was honestly a highlight of my graduate research experience to be able to connect with such an awesome and well-organized community of people who have so much appreciation for local geology. And I've worked in a lot of landscapes now and have yet to find anything quite comparable to IAFE that just brings together scientists and students and residents and lots of different people to connect over a shared love of geology. It really is something special. So I'll get into it. I'm going to be sharing some work that was very recently published, and what better audience to be the first to hear about this work. But this talk is going to go through some work I did in the channeled scabland, which is a landscape that I think many of you are probably pretty familiar with, but just in case anybody's not, I'll start with a brief introduction to the history and the geology of the channeled scabland. So the channeled scabland, the scabland part of the name is quite apparent from seeing the landscape from above. See, it's a very bare area in Washington, east of the Cascades. And we'll zoom in on the square here for a closer look. So during last ice age, a lot of this region was covered in fine glacial sediment called loess. And you can see that loess still present in some of the tan areas. And in a sort of a patchwork pattern, you can see that there's a lot of agriculture that is supported by this very fertile sediment. You can also see that in some places that loess has been removed to expose the basalt, the columnar basalt bedrock in the darker areas there.
I'll do this.
And if you were to go look around those darker areas at ground level, you would see that the surface of the basalt has been scoured. Places where there's still some loess has been eroded into streamlined hills in some places. And then, of course, there's the channeled part of the name, and you can see several large canyons in this landscape. And those canyons display giant waterfalls and contain depositional features comprised of very large pieces of sediment. And all of these features together look like things that you would find in a river. However, the amount of water flowing through the landscape today is far too little to be responsible for forming them. And this proved to be quite a puzzle for folks who were at the time working in the then very new field of geology. They were encountering these features which looked like they should have been formed by water, but they were quite a lot bigger than what you would encounter even in a modern river, and there wasn't really any
An archaeology thing?
source
It's a
of
geology thing, but they are. Don't mute.
Brett,
So there were a couple of early theories about how this landscape
she
formed.
got it all working nicely then.
But
Not really, I can't hear.
pause until everybody on Zoom. Okay. Oh, no, that's not gonna work. Okay, can people hear me on Zoom now? Is that all right? Okay, yes. All right. Let's keep rolling. So early in the history of studying this landscape, there were a couple of different theories that emerged about how this landscape came to be.
Here.
The one that eventually best explained all the available evidence was proposed, of course, by J. Harlan Bretz, who hypothesized that one or more large floods eroded the heck out of this landscape. And the story of how Bretz's theory came to be accepted is a great story, and turned out to be a very fundamental shift in the field of geology. But I'm going to leave that story for better storytellers than me to talk about. But anyway, in the mid 20th century, Bretz and others are starting to build up their case for ice age floods using stratigraphy, remote sensing, and very detailed mapping of the superficial geology and the topography to establish that glaciers had blocked rivers in the Northwest during the last ice age to create several glacial lakes. And those are here in dark blue on the slide. So the largest lake was Glacial Lake Missoula. And over the course of the last ice age, the glacial dam that was holding this lake back at the Purcell Trench ice slope would break up when the lake got to be too big or the ice got too weak. And this happened many times, probably over 100 times. And each of the breakups released large volumes of water in what are known as glacial lake outburst floods across the relatively unincised Columbia Plateau area. So the extensive erosion and the huge sedimentary features that the floods left behind allowed Bretz and the other geologists who followed him to learn quite a bit about the floods, despite the fact that the glaciers and the lakes they had formed had been gone for thousands of years. And so thanks to new computational and geochemical techniques, we can continue to build off of what Bretz began to find out more about how this landscape has been shaped by floods, as well as the role of giant outburst floods in shaping other landscapes across space and time. So thanks to the efforts of Bretz and many others who felt similarly drawn to figuring out this landscape, There's quite a bit that we feel pretty good about in our studies of how the channeled scabland formed. And a lot of those things that we have a little more confidence in have to do with totals. So like the total number of floods, which we can get from correlating depositional records onshore and offshore, the total area that was inundated by floodwater at across the whole interval of flooding, and that we can get a sense of from the sort of erosional and depositional features formed by shallow flows, pretty much at the limits of inundation. So those features which we call high water marks. We also have a fairly good idea of the total time interval of flooding. So that's been worked out by combining flood histories with age constraints on the lakes and the glacier activity. And other things that we've learned recently have to do with like the biggest thing, because that's what leaves the most enduring imprint on the landscape generally. So things like the peak flood size in certain places, the timing of the biggest flood, the biggest source of water. But there are still many things we're trying to still figure out. And many of those have to do with linking processes to features. So these are things like the relationship between the flood hydrology and the erosion of bedrock, or how the changing topography pushed and pulled floodwaters into the different tracts of the scablands. And this connection is very important because that is what allows us to extrapolate from what happened in the scabland to other landscapes where the preservation isn't as good, and lets us think about the kinds of impacts that maybe a future hypothetical flood could have in another place. So we wanted to learn more about the links between geography and process, and a really good place to do that is in Grand Coulee. So Grand Coulee is the biggest canyon in the scabland. Anytime I'm flying in and out of the Pacific Northwest, I look for it out the airplane window. It's a very good landmark, very easy to spot. And Grand Coulee is actually a complex of two canyons. So there's an upper part here, Upper Grand Coulee, to the north, and then to the south, there's the Lower Grand Coulee complex down there. And each of these canyon complexes was incised as a waterfall carved its way through the bedrock by eroding rock at a waterfall's edge. So this is an erosion mechanism that has been documented in multiple landscapes with similar geography and geology. And it's a process that's been also observed in laboratory scale experiments for simulating really high discharge floods that generate a lot of energy that exceeds the thresholds for erosion by plucking. So that's a process where like chunks of bedrock are getting ripped out of the ground. So erosion by waterfall retreat tends to produce canyons with a characteristic shape. So that those are things like uniform width, straight walls, and amphitheater-shaped heads, which are all characteristics we can see in Grand Coulee. And Bretz even recognized how conducive the columnar basalt bedrock in the channeled scabland would be to this type of erosion. He wrote in his 1932 paper on Grand Coulee that a receding waterfall mechanism would operate readily in the horizontal sheets of the Columbia basalt. All right, so to visualize this erosion process, because it's a little hard to wrap my head around, we're going to imagine water flowing over a more or less linear escarpment. So picture this diagram as like a bird's eye view of a landscape where water is flowing from the top of the screen to the bottom. And you have high topography like coming out towards you at the screen on sort of the upper part above the escarpment, and then below that you have low topography, so away from you. And it's those two topographies are separated by this ledge right here, this line. So as water's flowing from top to bottom, it's getting focused into the little irregularities or embayments along the ledge. And if the shear stresses exceed thresholds for plucking erosion, then the biggest embayments are going to start to grow until one of them can capture most of the flow. And that embayment can then erode even faster because it's attracting more water, generating higher shear stresses. So it can widen and it can lengthen until it reaches a width at which shear stresses along the sidewalls become too small for more erosion to occur. So then that canyon will continue to grow just by lengthening alone through upstream retreat of the waterfall, because the sides can't get any bigger, but you can still have erosion along at the head of the waterfall. So it sort of maintains a roughly uniform width as it extends itself. And this would mean that it's possible for high water marks formed by broader and shallower floods early in the sequence of events to then get abandoned as the canyon lengthens and is able to contain all the flow downstream of the head. So because of their uniform width, straight walls, and rounded heads, and also because we know a little bit about the bedrock geology in the channeled scabland, the canyons, of Upper Grand Coulee and Lower Grand Coulee are thought to have eroded by this waterfall retreat process. And the waterfalls would have initiated where floods are crossing a system of anticlines and synclines to the south for Lower Grand Coulee. And then for Upper Grand Coulee, the waterfall probably initiated right at the Coulee monocline there. And these folded rocks tend to be a little bit easier to erode than the rest of the bedrock because they're a little bit more densely fractured, all the folding. So the Lower Grand Coulee waterfall is still there. We call it Dry Falls today. And then the waterfall that formed Upper Grand Coulee actually eroded all the way past its drainage divide with the Columbia River. So it eroded itself into oblivion. And all that's left is the waterfall is this feature called Steamboat Rock here, where the eroding waterfall sort of bifurcated and then reconnected upstream as it eroded and left this little island of pre-flood topography in its wake. So because Grand Coulee preserves so much information about its past in just its shape alone, what we wanted to do was bring together 3 different techniques to learn when and how fast this intense incision that formed Grand Coulee took place. And we also were interested in this because we wanted to know how unique its erosional history is compared to other canyons in the scablands and also around the world. So, of course, the first technique always has to be looking at the landscape itself. So going through things like finding the sizes and compositions of sediment that was transported by floods, going through mapping high water marks to find the ultimate limits of inundation, or doing topographic analyses. But just as there are geological constraints that tell us about the limits of the flood's energy and extent, there are also some physical limits imposed by things like fluid dynamics and conservation of mass. And those provide insight into flood behavior when we replicate the movement of water in 2 dimensions over time. And that's what we get from computer simulations, which we call modeling. And then, because this is the scabland where everything is extra complicated, because we're dealing with multiple floods of different sizes along different pathways, we also use geochemical dating techniques to figure out the timing of important milestones in this sequence of events. So each technique here imposes certain limits on the others so that we can start to refine the history of Grand Coulee into something that's detailed enough to start comparing with other places and situations. So let's start with the question of when the erosion of Grand Coulee took place. So the preferred route for floods from Glacial Lake Missoula would have been to travel down the Columbia River, shown there outlined in green. But once the ice advanced far enough to block that route, Glacial Lake Columbia starts to form, and incoming floods were forced to go over the next highest drainage divides to the east. So going from west to east, we have Moses Coulee in orange, which can be inundated by flows from Columbia Valley or out of Upper Grand Coulee's west bank prior to when Grand Coulee's erosion took place. So then we have Grand Coulee here in yellow. And today, Grand Coulee is the lowest drainage divide elevation, but before it eroded, it would have been 200 to 250 meters higher. Next in red, we have the Telford Creek, Crab Creek tract. And that's a stretch of broad flows which go over the highest drainage divide, about 709 meters today. And then we have in purple the easternmost tract, the Cheney-Palouse in purple, and that's another sort of section of these broader, shallower flows. So Bretz initially hypothesized that it would have taken more than one glaciation to incise Grand Coulee, mostly because it was so big. And then the lack of depositional evidence for a deep glacial Lake Columbia kind of pointed to this as well. However, no flood deposits older than the last ice age have been documented at Grand Coulee, and recent hydraulic modeling suggests that Upper Grand Coulee was probably closed during the earliest Missoula floods. So our main question was, when did the incision of Grand Coulee take place? And we also were hoping to find some other important controls on the sequence of events that shaped this landscape, such as when Glacial Lake Columbia was at its highest level and when some of these other eastern flood routes were active. So we want to find the age of the most recent floods in different places along all of these flood routes. And so we use geochemical dating techniques to sample boulders which interacted with floods or glaciers in different ways using beryllium-10 exposure dating. So exposure dating uses the buildup of isotopes that happens at a very predictable rate to say how long something has been exposed at the Earth's surface. It's a pretty cool technique, kind of blows my mind a little bit that it works, but they tell me it does. But what happens is cosmic rays cause a small fraction of gases near the top of the atmosphere to undergo nuclear reactions. The products of those reactions cause other reactions further down in the atmosphere, and so on until they reach the Earth's surface, and it reacts with solid material on the ground. So these reactions only happen in the top meter or so of the Earth, The ground is solid, it's harder for things to travel. And it's a process it's going on around us all the time, but only generating very, very tiny amounts of these isotopes. Even so, it's enough for us to measure for things that sit on the surface for a very long time, a couple of thousand years or so. And the longer something stays exposed there, the more of these isotopes build up in the material. So you can use different isotopes to do this. The one we use is beryllium-10 because our target is these erratic granite boulders transported by floods or by icebergs from upstream. So granitic sediments are indicative of flooding in the channeled scabland because the bedrock exposed at most of the surface of the Columbia Plateau is pretty much entirely basalt. So any granite we find would usually have to be transported from somewhere else by something like a flood or a glacier. And in granite, the beryllium-10 isotope gets produced from the oxygen in quartz minerals, and granite contains a lot of quartz, so that's a nice choice for us. So when we take a sample, we break a chunk off of the tops of boulders using a masonry drill to sort of place little wedges into the rock in sort of a cone shape. And then we hammer those wedges into the rock to propagate the cracks and allow us to break off about 1 kilogram of material from the boulders. And I would love to just show you lots of pretty pictures from our field work for the rest of this talk. What I've done instead, though, is to put all of our sample photos onto a Google Earth map, and you can access it at the QR code here or by following the link that's on the slide. So each of the pins on the map represents a sample that someone collected for exposure dating. We have our samples on here, along with some from other researchers who have worked in other parts of the scabland, like along the Columbia River. And we ended up contributing 28 new samples from some of the eastern flood routes, which we then brought back to process in the lab at UMass Amherst. So to get beryllium out of this kilogram of boulder, we have to get rid of everything that's not beryllium. And we do that using a sequence of physical and chemical separation methods. So first, it's a long process, takes many months. To start, we crush the boulder to a grain size that will separate the rock at mineral boundaries. So we're turning this chunk of solid rock into sand, basically. And then we remove some of the minerals that we don't want using magnets and other physical methods like density separation and froth flotation. At this point, it's mostly quartz left. So we etch the sample in hydrofluoric acid to purify it. And once we have a really clean quartz sand, we dissolve it in extra strong hydrofluoric acid. And we add a known amount of beryllium-9. That's the stable isotope of beryllium. So then we collect all of the beryllium by rinsing it with a series of solutions that will pick up all the other elements one at a time. And then we dry what's left into like a pellet that we burn to turn it into beryllium oxide. And that pellet gets packed into these tiny cathodes that get shipped to a mass spectrometer, and that can measure the ratio of beryllium-10 to beryllium-9 very, very precisely. And because we know how much beryllium-9 we added to the sample, we can calculate how many atoms of beryllium-10 we have, and we turn that into an exposure age, or more precisely, a probability distribution that the boulder we've sampled is a certain age. And we also factor in things like how much the topography around the boulder would have shielded it from incoming cosmic rays. Also things like the latitude and the elevation that the boulder was sitting at, which can also affect the dosage. And so this is what that age distribution looks like. It'll get bigger later. So each one of the thin lines here represents the age distribution for a single sample. You have the age in thousands of years on the horizontal axis there. And the peak of each curve represents the most likely age of that sample. So when the age distributions overlap very nicely like that, we can say with a pretty good amount of confidence that the boulders in this population that we sampled were deposited during a very narrow time frame. In the case of this sample, between 16.7 and about 17.1 thousand years ago. And we do that by essentially summing all of the small curves to get an age distribution for the entire population, which is the thick line up there. And we can tie these curves to the landscape history because part of our sampling criteria is to only select boulders with clear evidence of the process that we're interested in. So for instance, if we care about dating the flood timing, we'll maybe look for boulders with things like a rounded shape indicating abrasion in water, or percussion marks indicating like high-speed collisions with other particles. So we do this for all of the groups of boulders that we sampled throughout the scabland, with each row on this diagram representing a different event or location that we're targeting. And you can see that while the age distribution in some of the areas that we sampled overlap very well, like that one here in the bottom, some others are a little bit less consistent. And in some cases, this is because there just weren't a lot of suitable granite boulders in that particular area. That was the case in Moses Coulee, where we walked around for days and ended up just finding two sad little boulders. But in other places, like in the Cheney-Palouse area, this larger age spread might actually represent a longer window of flooding along that route, because the individual ages are all quite different from each other. But we really have to put this data on a map to start making sense of it. So I'll walk through the different populations that we sampled and what they tell us about the history of this landscape when we put them together with age constraints on other components of this system, including Glacial Lake Columbia and the Cordilleran ice sheet. So the earliest and probably the biggest floods went down the Columbia River about 17,000 years ago, before the glaciers advanced far enough to block the Columbia. So inundating the highest erratics along the Columbia River right here requires that Upper Grand Coulee is not yet in size, which I've indicated by shading the canyon in there. Because flood models of the entire Missoula flood route show that Grand Coulee, if it's at its present elevation, kind of siphons off too much water away from the main Columbia River route to inundate those erratics on the Columbia River there. And we also see from dating in the Cheney-Palouse that some of the early floods may have also inundated that easternmost pathway as well. So now moving forward to around 16 to 14.5 thousand years ago, the Columbia River is now blocked by glaciers, and that forces floods to start going over these eastern flood routes. And it establishes Glacial Lake Columbia at a stable height of about 680 meters. That elevation is controlled by the elevation of the bedrock left at Upper Grand Coulee. So this is when we start now getting floods entering the Grand Coulee route, and that's when Upper Grand Coulee starts being able to erode as well. So starting at the Coulee monocline there and working its way northward via that waterfall retreat process. Since the northern portion of Upper Grand Coulee is the last bit to erode, floods can still enter Moses Coulee over here via Foster Coulee on Upper Grand Coulee's west bank, and possibly through other routes to the north as well. So the Okanagan Lobe continues now to advance to block Upper Grand Coulee at its maximum extent, and that raises the stable height of Glacial Lake Columbia to around 730 meters. And this happens by about 14 to 15,000 years ago. So now is when incoming floods can get over the Telford Crab Creek tract, as well as probably around the eastern rim of Upper Grand Coulee through Northrop Canyon. So Upper Grand Coulee would have to be fully incised by this point because distinctive glacial sediment and erosion patterns have been documented on the inside wall of Upper Grand Coulee, sort of close to Steamboat Rock. So that means that the ice would have to advance after the erosion takes place. And then the Okanagan Lobe starts to retreat from its maximum extent at Withrow Moraine around 14,000 years ago, with floods able to now get out over the through Upper Grand Coulee now that it's not full of bedrock or glacial ice. It has a drainage divide at about 470 meters, basically what it is today. So now that's the lowest outlet for Glacial Lake Columbia, and the last Missoula floods probably drain out through Upper Grand Coulee. The very last floods is then when the Okanagan Lobe pulls back from the Columbia River entirely, letting Glacial Lake Columbia drain out that way, and potentially some other smaller glacial lakes along that route as well, around 13,000 years ago. All right, so a lot of this interpretation builds off of age constraints established by others. So what does our piece of the puzzle add to the overall story of this landscape, other than just improving our confidence in those previously established benchmarks? Well, one interesting thing is that now we have some geochronology support for an observation from flood simulations that the U.S. Geological Survey did, which is that you can expect floods down the Cheney-Palouse tract at just about any time during the last ice age, regardless of the erosional state of Grand Coulee. And we probably need to sample more ice-rafted boulders along the Cheney-Palouse route to say this for sure. But our widespread of ages in the Cheney-Palouse tract sort of adds an extra layer of plausibility to that idea. So then over in Telford Crab Creek, we also dated a few ice-rafted boulders that were at higher elevations than the highest stable Glacial Lake Columbia height of 730 meters at that time. So that means that they were probably carried in by Missoula floods entering Glacial Lake Columbia while it was at its very highest stable level. So the ages we get from those boulders of about 14.8 thousand years lines up very well with ages measured at Withrow Moraine that indicate that the Okanagan Lobe starts to retreat around 14 to 15,000 years ago. And its similarity to the end of erosion in Upper Grand Coulee around 15.2 thousand years ago suggests that there was not that much time between the last bit of erosion in Upper Grand Coulee and the subsequent advance of ice into the canyon. So maybe there was only on the order of centuries or less between the erosion and the ice moving in. So over to the west, Moses Coulee received floods from glacial Lake Missoula at some point during the last ice age, which we know from work comparing the geochemistry of granite erratics with the rocks near glacial Lake Missoula. But from the USGS modeling, we see that if Upper Grand Coulee is fully incised, there's no way to get a Missoula flood into Moses Coulee from that route. And floodwaters would not have come close to overtopping the east rim of Upper Grand Coulee. So the age constraints that we have in Moses Coulee, as well as on the east rim of Upper Grand Coulee, point to ongoing incision in Grand Coulee still between 17.5 and 15.5 thousand years ago. And we also have a somewhat looser, but I think still fairly convincing limit on the beginning of erosion in Upper Grand Coulee. And that's from a flood bar where flow spreads out south of the Coulee monocline, right here in a place, an expansion bar called Heartline Bar. So the gravel that makes up this bar appears to be pretty much entirely basalt, and that's in contrast to some other bars in the area, like the Ephrata Fan and Payne's Gulch Bar along the inside of Upper Grand Coulee. And those bars contain large granite boulders. So the bedrock exposed at the surface of the Grand Coulee area is mostly basalt, but under that basalt is some granite bedrock, and that granite was uncovered on the floor of Upper Grand Coulee in sort of the northern half. You can see up here in Steamboat Rock, you have basalt overlying the granitic rock. And that gets uncovered once the waterfall sort of erodes past that point and starts to uncover it. And that's the source of the granite in these other two bars. So the lack of granite mixed in with the basalt in Heartline Bar means to us that the eroding waterfall must not have yet reached the northern half or so of Upper Grand Coulee at the time when Heartline Bar formed. And the other thing about the gravel on this bar that's interesting is that it appears to be very unweathered compared to some of the other bars that we know of that are older. And in fact, Brett's described the sediment on this bar as being almost perfectly fresh. And that all points to the bar being formed no earlier than the last ice age. But as Brian Atwater documented through very meticulous sedimentary work, there were at least 89 floods that entered glacial Lake Columbia while it was still blocked by ice. So an intriguing implication of a last glacial erosion time frame of Upper Grand Coulee is that if Upper Grand Coulee's incision all takes place during the last ice age, that would mean that there are 89 whole floods from glacial Lake Missoula that did not contribute any significant erosion to forming this very, very large canyon. So, okay, from the dating results, it seems possible, maybe even likely, that Grand Coulee was carved entirely during the last ice age. But this offers some new opportunities to see if it holds up against other lines of evidence. So a lot of effort has been dedicated in the last couple of decades to correlating depositional evidence in different parts of the Missoula flood pathway. And this has resulted in an estimate that there were about between 100 and 110 floods that came out of Glacial Lake Missoula. So if 89 of those floods post-date the incision of Grand Coulee, meaning they didn't really contribute to the canyon's incision, one way we can test our young Grand Coulee hypothesis further is to see if it would be possible to evacuate all of the bedrock from Upper Grand Coulee in about 20 floods or less. So next we'll consider the question of how fast Upper Grand Coulee eroded. So when we're talking about a changing landscape, the implication is that there was some initial state, then there was modification, in this case by erosion, and then you get to some final state. And we can see the modern state of the landscape if we go take a drive out to Grand Coulee and walk around. But if our unknown is the process, then we have to first reconstruct the pre-flood state of the canyon. So essentially filling up the canyon back with the missing volume of bedrock. And if this were a narrower valley, what we might do is just interpolate a flat plane between the two walls of the canyon. But Grand Coulee it's big, it's hundreds of meters wide, and so for that large of an area, we try a more complicated approach. And we can do this because we have some guidance from the landscape about what it looks like prior to floods. The landscape adjacent to the canyon is actually still fairly similar to what it probably looked like before the floods, and it preserves, importantly, portions of the pre-flood stream network. So we can see where that pre-flood stream network was kind of cut off by the erosion of the canyon. This one's a nice view of Lower Grand Coulee here. But we can sort of trace the path of those pre-flood channels back into the canyon to reconstruct the missing chunk of the topography. So the idea behind using the pre-flood drainage network is that streams tend to develop concave up profiles that can be described pretty nicely by a logarithmic equation. So this means we can extrapolate the missing portion of a stream's profile by fitting an equation to the intact portion. So if this is a stream profile before the floods, it's like if you're walking along, your elevation is on the y-axis and the distance you've walked is on the x-axis. And then you have floods that come along and they erode the bedrock really rapidly just in their path. And so the tributaries that used to drain into the canyon suddenly don't have enough energy to adjust to the new lower canyon floor. And so they just kind of persist in the landscape as those hanging tributaries perched up on the rim there. So we extract the elevations along a portion of the tributary upstream of where it intersects the canyon rim. We fit the logarithmic equation that best fits that portion of the profile. And then we just extend that back downstream toward the center of the canyon to get a pre-flood channel floor elevation represented by the red dot there. And if we do this for a lot of tributaries, we can get a nice little pathway of lots of red dots, and we can use that to build a line of elevations down the deepest part of the upper Grand Coulee pre-flood channel that would have existed before the Missoula floods started eroding the bedrock there. And actually, we reconstruct two pre-flood channels, one flowing south and one flowing north, because remember the floods are overtopping a drainage divide, separating the north flowing and the south flowing channels. And then we interpolate 2D topography between the channel, the pre-flood channel profile that we just rebuilt, and the topography outside of the canyon walls to get a 2D map of topography that represents the pre-flood state for the whole canyon. And then the total elevation difference between the modern topography and the pre-flood topography gives us an estimate of the eroded volume, and that comes out to something like 68 cubic kilometers. So next we can turn to hydraulic modeling to find the smallest discharge that inundates the high water marks on the pre-flood topography. So we let water come in our models in the upstream end of the canyon. It's allowed to flow throughout the domain and exit at outlets. And what we do is we test a range of constant discharges. So we start one and then we wait for it to reach steady state. And then we check to see whether it reaches the high water mark, which in Upper Grand Coulee, we chose one that's a low drainage divide, displaying evidence of scour by flooding. So if it doesn't quite inundate that high of an elevation, we ramp up the discharge a little bit and check that again to just sort of iteratively find the discharge that barely inundates that high water mark. So here you can see the high water mark and the inundated extent in the black line there that we get from the smallest discharge to hit that spot on the landscape. And that discharge is 3.1 million cubic meters of water per second. This is kind of a difficult number to visualize. So for reference, it's about 10 times bigger than the average discharge of the Amazon River, about 100 times bigger than the average discharge of the Mississippi. Bottom line, it's a lot of water. So now we have to turn this discharge into the number of canyon carving floods. So our approach is going to be to use sediment transport rates to estimate how long it would take to move the missing volume of bedrock once it becomes sediment. Because remember, we have the difference in volume between the pre-flood topography and the modern topography from our reconstruction process. One nice thing about this approach is that you don't have to assume a particular erosion process at all. All you need is a grain size, which you get from going out in the field and measuring a bunch of bits of sediment. We can easily test a range of grain sizes with this approach as well. And we also need a shear stress, and we get that from our models. So the discharge that we want to use is the one that barely inundates the high water marks. So that's going to be the 3.1 million cubic meter per second number. But now the topography that we want is actually going to be the modern topography, because that's what the floods are going to encounter just downstream of where the erosion is actively occurring. So we run another set of models representing those conditions, and we average the shear stresses in the downstream end of the canyon. And those shear stresses come out to be around 2,000 pascals For reference, the estimated shear stress for stripping large vegetation like trees and shrubs out of a riverbank is something like 350 pascals. So, all right, now I'll just summarize the calculations that we do to get from this shear stress distribution to the minimum number of floods you would need to erode Upper Grand Coulee. So we start by estimating the bed load flux using the shear stresses that we got from our models and a grain size that we get from boulder sizes that we measure in the field. So this is the rate at which the larger pieces of sediment are moving in the flood by bouncing along the bed, which is proportional to the shear stress of the moving water. Next, we calculate the amount of suspended sediment. So those are going to be the smaller pieces floating along in the upper layers of the flow, which we estimate using a ratio of suspended to bedload sediment calculated from the approximate volumes of offshore fine-grained deposits to the coarse-grained terrestrial flood deposits. That works out to be about 8.3. And then we add those together to calculate the total sediment volume flux through the canyon. We multiply it by the average width of the canyon in that reach where we pulled out the shear stresses. And then we divide the missing volume of bedrock by that flux, the transport rate, to get the total time it would take to move all of that volume. And lastly, we divide that time by the duration of the high energy portion of a single flood, which from USGS models is estimated to be around 100 hours to get an approximate estimate of the number of floods. So based on the sediment transport rates, we estimated that it would take about 5 to 7 floods to incise Upper Grand Coulee. We actually did this exercise for Moses Coulee as well, where we found a similar range of about 4 to 8 floods there. So again, correlating offshore and terrestrial flood deposits along the entire flood route has revealed that there were about 100 to 110 total floods from glacial Lake Missoula. However, this count includes floods that took other routes through the channeled scabland that bypassed Upper Grand Coulee, as well as the deposits that are sitting there on the floor that post-date the erosion in that canyon. So Upper Grand Coulee has a lot of deposits from these sort of smaller, later flood activities. But the record in Moses Coulee is a little bit more tightly constrained and points to at least 4 floods down that route, very nicely matching our estimate of 4 to 8 floods in Moses Coulee. And we also find that our estimates are pretty nicely bracketed by the number of specifically high energy floods that were worked out from the elevations of high water marks further downstream in the Columbia Gorge, which is a place that didn't experience quite as much erosion from the Missoula floods as Upper Grand Coulee did. So the number of floods that we estimate is turns out to be only or less than 10% of the estimated total number of floods from glacial Lake Missoula, which means that perhaps it's possible that only a handful of the floods actually contributed to eroding the canyon. So if we assume that each of those floods contributed about equally to incising the canyon, we can also ballpark some erosion and waterfall retreat rates. And those work out to be on the order of hundreds to thousands of cubic meters per second for erosion rates, and hundreds to thousands of meters per day for retreat rates. And these are quite a bit faster and higher than any example we know of on Earth today, even in canyons that have eroded in a similar fashion. For instance, a dam break flood in Texas a couple decades back that incised 7 meters back over 3 days of flooding, as well as canyons in Iceland that are prone to flooding, where erosion rates have been estimated to be hundreds of meters over several days. However, the Missoula floods had discharges estimated to be quite a lot bigger than any of these other examples. So we're starting to get the sense that perhaps erosion becomes increasingly efficient at higher discharges for extreme floods over similar types of bedrock. So based on how long it would take to move all of the missing rock out of Upper Grand Coulee, we think that this canyon could have been carved by as few as 5 to 7 floods, which is well within our limit of 20 or fewer floods to reconcile with a last ice age incision of Grand Coulee. And that's even taking into account the smaller flood sizes we would expect if we factor in the space taken up by all the bedrock that eventually gets eroded to form Upper Grand Coulee. Also because exposure ages suggest that Upper Grand Coulee was carved entirely during the last ice age, we think it's pretty likely that Upper Grand Coulee was incised exceptionally fast. Many more floods would pass through Upper Grand Coulee after it was incised, but if all the erodible rock was removed after the first few floods, those later floods were probably just conveyed down the canyon without inflicting too much erosional damage, as was the case along much of the Columbia River. And considering what this would mean beyond the scabland, Grand Coulee suggests that giant outburst floods are exceptionally powerful agents of erosion, particularly in places with geology and geography that is especially susceptible to erosion via a retreating waterfall, which the columnar basalt and the mostly but not entirely flat topography in the region that eventually became Upper Grand Coulee definitely is. And this is a really important thing for us to know today, because globally, man-made dams are getting bigger, and the risk of dam failure in both natural and man-made reservoirs is increasing, largely due to climate change. And so Grand Coulee has shown us that in certain environments where the geology and the geography are just right, we're probably underestimating the impact to the landscape that outburst floods might be capable of. So I'll leave it there and thank my advisors, my mentors, colleagues who have supported this work, and another big shout out to IAFI for making all of this work possible. Thank you all for listening, and I'm very excited to continue discussing this and hear all your questions.